welcome to this problem walkthrough. Today, we'll explore an interesting coding challenge, problem number 357, count numbers with unique digits. This problem tests your understanding of combinatorics and efficient enumeration techniques. Let's dive in and uncover the solution step by step. In this problem, we are tasked with counting all numbers that have unique digits, given an input n. The numbers can have at most n digits. For example, if n is 2, we need to count all numbers that are either 1-digit or 2-digit long, or no digit repeats within each number. The input is a single integer n that ranges from 0 to 8, and we need to return an integer representing the total count of such numbers. Let's consider a specific example. If n equals 2, the output is 91. This means there are 91 numbers with up to 2 digits where all digits are unique. Now, let's break down the logic for the example where n equals 2. For this case, we need to count all numbers with up to 2 digits that have unique digits. First, we consider 1-digit numbers. These are simply the numbers from 0 to 9, giving us 10 numbers in total. Next, for 2-digit numbers, the first digit can be any digit from 1 to 9, which gives us 9 choices. The second digit can be any digit from 0 to 9, except for the first digit, leaving 9 remaining choices. Multiplying these, we find there are 9 times 9 is equal to 81 2-digit numbers with unique digits. Adding the 10 1-digit numbers to these 81 2-digit numbers, we arrive at a total of 91 numbers. Additionally, if n equals 0, the only number we can form is 0, so the output in that case is just 1. Let's now consider a slightly larger example where n equals 3. Here, we count all numbers with up to 3 digits that have unique digits. As before, the 1-digit numbers are 0 through 9, giving us 10 numbers. For 2-digit numbers, we already know there are 81 based on the same reasoning we just discussed. For 3-digit numbers, the first digit can be any digit from 1 to 9, giving us 9 choices. The second digit can be any digit from 0 to 9, excluding the first digit, leaving 9 choices. The third digit can be any digit from 0 to 9, excluding the first 2 digits, leaving 8 choices. Multiplying these, we find there are 9 times 9 times 8 is equal to 648 3-digit numbers with unique digits. Adding these together, we get 10 plus 81 plus 648 is equal to 739 numbers in total. So, when n equals 3, the output is 739. Finally, let's look at the constraints and some edge cases. The input n must be between 0 and 8. For values of n greater than 10, the count remains the same as for n equals 10, since numbers with more than 10 digits will inevitably have repeated digits. For example, if n equals 0, the count is always 1 because the only valid number is 0. If n equals 1, the count is 10, as all single-digit numbers from 0 to 9 are unique. An important observation is that the number of valid choices for each digit decreases as we move to the rightmost digits, which is similar to a factorial pattern. This allows us to solve the problem efficiently using combinatorics, either through an iterative approach or a mathematical formula tailored for this factorial-like behavior. To tackle this problem, one straightforward approach is the brute force method, where we directly enumerate all possible numbers with up to n digits and check if each number has unique digits. The intuition here is simple. For each number in our range, we convert it to a string and use a set to verify if all its characters are distinct. If they are unique, we count that number as valid. While this method is conceptually easy to understand, it's computationally expensive. The total number of candidates grows exponentially with n, as we are essentially iterating through a range of 10 to the power of n. The time complexity ends up being 10 to the power of n asterisk k, where k is the average number of digits per number, and the space complexity is k, for the set used to check uniqueness. While intuitive, this approach becomes infeasible for larger values of n, such as 8, due to the sheer number of calculations involved. A more efficient solution leverages mathematical counting using combinatorics to avoid generating all numbers explicitly. The key insight here is to directly count numbers with unique digits by analyzing the available choices for each digit. For instance, when n equals 0, there's only one valid number, 0. For n equal to 1, we have 10 valid numbers, ranging from 0 to 9. When n equals 2, we can pick the first digit in 9 ways, since it cannot be 0, and the second digit in 9 ways, avoiding repetition of the first digit, giving us 9 times 9 is equal to 81 unique numbers. Extending this logic to n equals 3, the first digit has 9 options, the second digit has 9 options, and the third digit has 8 options, resulting in 9 by 9 by 8. This pattern continues as the number of choices decreases for each additional digit. By summing the counts for numbers with up to k digits, where k ranges from 0 to n, we can calculate the total unique numbers. The formula builds incrementally, starting with 1 for n equals 0, then adding 9, then 9 by 9, and so on. To implement this optimized approach, we start by initializing a total variable to 0 and another variable unique underscore digits to 9, representing the available choices for the first digit. Then, we iterate from k equals 1 up to n. For each k, we calculate the count of unique numbers using the formula, accounting for the decreasing choices with each additional digit. We then add this count to the total. This approach is highly efficient, with a time complexity of O(n), since we needed most 8 iterations for n up to 8. The space complexity is O(1), since we don't use any additional data structures, relying only on a few variables. While this method is mathematically driven and requires a deeper understanding of combinatorics, its efficiency makes it a clear choice over brute force. By focusing on the decreasing choices for each digit, we skip unnecessary computations and achieve a scalable solution. In conclusion, the mathematical counting approach is the optimal solution for this problem due to its efficiency and scalability. Although the brute force method is more intuitive, it becomes computationally impractical as n increases, making it unsuitable for larger inputs. The optimized approach, on the other hand, uses mathematical insights to compute the result in linear time, leveraging the pattern of decreasing digit choices. While it may require a bit more effort to understand combinatorics, the significant performance benefits far outweigh this minimal trade-off. This balance of clarity and performance makes the mathematical counting method the ideal strategy for solving this problem effectively. In this problem, our goal is to count all the numbers with up to n digits such that each number has unique digits. For example, if n is 2, valid numbers would include 10, 12, and 21 because each digit appears only once. On the other hand, numbers like 11 or 22 would be invalid due to repeated digits. To solve this, one approach is the brute force method of direct enumeration. We start by defining the range of numbers to check. For a given n, the range is from 0 to 10 to the power of n1. We also initialize a counter, count, to 0, which will track the total number of valid numbers. Next, we iterate through all integers within this range, converting each number into a string representation. This conversion makes it easier to access individual digits, as we can treat them as characters in the string. For instance, the number 123 becomes the string 123, allowing us to perform operations like checking for uniqueness efficiently. Once we have the string representation of a number, the next step is to check whether its digits are unique. To do this, we create a set from the string of digits. A set inherently removes duplicates, so if we take a number like 112, its set representation will be 1, 2. By comparing the length of the set with the length of the original string, we can determine if all the digits are unique. If the lengths are the same, it means there are no repeated digits. If not, the number contains duplicates. Each time we find a number with unique digits, we increment our counter by 1. Once all numbers in the range have been processed, the final value of the counter gives us the total count of valid numbers with unique digits. Now, let's delve into some of the key insights behind this approach. First, why do we convert each number to a string? The reason is that accessing digits as string characters is simpler and more intuitive than using repeated modulo and division operations. This makes the implementation cleaner and easier to understand. Next, why use a set? A set is ideal because it automatically removes duplicate entries, which saves us from writing additional logic to check for repeated digits. By simply comparing the length of the set with the string, we can verify uniqueness with minimal effort. In terms of complexity, the time complexity is determined by the number of integers we process. With 10 to the power of n numbers in the range, and each conversion and set operation taking O(n) time, the total complexity becomes O(n) asterisk 10 to the power of n. The space complexity, on the other hand, is O(n), as we only need to store the string and set representation for each number during processing. To implement this algorithm, we rely on two primary data structures, sets and strings. A set is crucial for verifying the uniqueness of digits since it inherently removes duplicates, making it both efficient and straightforward. Strings, on the other hand, simplify the process of digit extraction. By converting numbers to strings, we can directly iterate over their digits, making it easier to use them with sets. To see this in action, let's consider an example where n equals 2. Here, the numbers to check range from 0 to 99. For the number 12, we convert it to the string 12, which gives us the set 1, 2. Since the lengths match, we count it as valid. For 11, the string 11 results in the set 1, where the length mismatch indicates repeated digits, so we skip it. By repeating this process for all numbers, we find that 90 out of the 100 numbers in this range have unique digits. Finally, let's discuss some optimizations and edge cases. One optimization is early termination during set creation. If we detect a repeated digit while adding to the set, we can immediately skip further checks for that number, saving time. Another optimization is to handle leading zeros. Numbers like 01 foot can be treated as 1 to avoid unnecessary duplication. For edge cases, consider n equals 0. Here, the result is 0 because no numbers exist with 0 digits. For n equals 1, all single-digit numbers from 0 to 9 are valid since there are no repeated digits. Lastly, for large values of n, such as 10, it's important to ensure that the algorithm handles the computation efficiently without running into memory or performance issues. These considerations help make the solution both robust and scalable. This Python implementation solves LeetCode problem number 357, count numbers with unique digits. The objective is to compute all numbers with unique digits for a given number of digits n. The solution starts by addressing the simplest case. When n equals 0, the only valid number is 0, so we return 1. For n equals 1, there are exactly 10 valid numbers, 0 through 9. The count variable is initialized to 10, representing the count of unique numbers for n equals 1. We then define two additional variables, unique_digits, which tracks the product of available digits for forming unique numbers, and available_digits, which reduces as we select digits for constructing numbers. The loop iterates from 2 to n, inclusive. For each iteration, we calculate the number of unique numbers that can be formed by multiplying the current unique_digits with the remaining available_digits. This product is added to the running count. After each iteration, the available_digits is decrement, as fewer digits remain available for subsequent positions. This approach ensures that we account for all valid unique digit numbers without redundantly enumerating them. It is efficient, as the number of operations is proportional to n, making the time complexity O, n. The final result, stored in count, is returned after the loop concludes. This implementation handles edge cases, including n equals 0 and large values of n, capped at 10, since there are only 10 digits. This is the Java implementation of LeetCode problem number 357, count numbers with unique digits. The logic mirrors the provided Python solution, with type declarations and a main method for testing. The method iteratively calculates the count of numbers with unique digits for a given integer n, starting with the base cases and reducing available digits step by step. Java-specific features like explicit type declarations are used for clarity and correctness. To begin, let's look at the simplest case where n equals 0. When n is 0, the problem specifies that the only number we can form is 0 itself since we're not allowed to use any additional digits. This means the output is straightforward, it's simply 1, as there is only one valid number, which is 0. Moving to the next example, where n equals 1, we initialize the count to 10. This accounts for all single-digit numbers, ranging from 0 to 9. For a single-digit number, there are no restrictions beyond choosing one digit, so the output is 10. At this point, we can see that the count starts considering numbers with unique digits in subsequent examples, but for n equals 1, we don't iterate further and directly return 10 as the output. Now let's explore the case where n equals 2. We start with the same initial count of 10, which represents all single-digit numbers. At this point, we also initialize two state variables, unique_digits to 9, representing the 9 choices for the first digit, 1 through 9, excluding 0, and available underscore digits to 9, representing the remaining digits available for subsequent positions. When we move to I equals 2, meaning we're forming 2-digit numbers, we calculate the number of valid 2-digit numbers with unique digits by multiplying unique underscore digits by available underscore digits. This gives us 9 times 9, which equals 81. Here, the first digit has 9 options, and the second digit also has 9 options since it cannot repeat the first digit. We then add this 81 to the existing count, bringing the total count to 91. Finally, we decrement available underscore digits to 8, as we've used another digit, limiting the options for subsequent numbers. After completing the iteration for I equals 2, the updated state is as follows. The total count is now 91, the current value of unique underscore digits is 81, and available underscore digits has been reduced to 8. Since n equals 2 in this case, the loop ends here, and we return the final count of 91. Now, if we increase n to 3, we again start with an initial count of 10, reflecting all single-digit numbers from 0 to 9. As before, we set unique underscore digits to 9, the number of choices for the first digit, and available underscore digits to 9, the total digits available for subsequent positions. For I equals 2, we follow the same process as before. We calculate unique underscore digits by multiplying it with available underscore digits, resulting in 9 times 9, which gives us 81 2-digit numbers with unique digits. Adding this to the count brings the total to 91, and we reduce available underscore digits to 8. Next, for I equals 3, we extend this process to 3-digit numbers. We multiply the current unique underscore digits value of 81 by the remaining available underscore digits, which is 8. This gives us 648 valid 3-digit numbers where all digits are unique. Adding this to the running total count, we get 91 plus 648, which equals 739. Finally, we decrement available underscore digits to 7 as one more digit is now restricted. After completing the iteration for I equals 3, the updated state shows that the total count is 739, unique underscore digits is 648, and available underscore digits has been reduced to 7. Since n equals 3 in this case, the loop terminates, and we return the final count of 739. This result represents the total number of unique numbers that can be formed with up to 3 digits, or all digits within each number are distinct. This systematic approach ensures we account for all possibilities while adhering to the uniqueness constraint for the digits. To analyze the time complexity of the function count numbers with unique digits, we start by breaking down the operations step by step. First, consider the base case where n equals 0. In this scenario, the function simply returns 1, which is a constant time operation, or O1. Next, during initialization, variables such as count, unique underscore digits, and available underscore digits are set up. These initializations also take constant time, contributing O1 to the overall complexity. Now, the main computational work happens in the for loop, which iterates from I equals 2 up to I equals n. This means there are at most n1 iterations. Within each iteration, 3 operations are performed: a multiplication to update unique underscore digits, an addition to increment count, and a subtraction to decrease available underscore digits. All of these are constant time operations. Therefore, each iteration of the loop performs O1 work, and the total work done by the loop depends directly on the number of iterations. When we account for the loop's n1 iterations, the total contribution of the loop becomes O(n). Adding this to the constant time operations from the base case and initialization, the overall time complexity of the function is O(n). Now, moving to space complexity, we analyze the memory usage. The function uses a fixed number of variables, such as count, unique underscore digits, available underscore digits, and the loop counter I. Since these variables do not grow with the size of n, they occupy constant space, or O1. Additionally, there are no auxiliary data structures like arrays or lists being allocated during the execution of the function. This means no extra memory is used beyond the fixed set of variables. In conclusion, the space complexity of the function is O1, making it highly efficient in terms of memory usage. To better understand the efficiency of this approach, let's compare it to a brute force solution. In a naive method, we would generate all possible numbers up to 10^n and check each one for unique digits. Generating these numbers would involve creating up to 10^k numbers for a given n equals k, leading to a time complexity of 10 to the power of n. On top of that, verifying whether each number has unique digits requires examining each digit, which would take k time for a number with k digits. Multiplied across all numbers, this adds another k asterisk 10 to the power of k factor to the time complexity. This exponential growth makes the brute force approach computationally expensive and impractical for larger values of n. In contrast, the efficient approach avoids the need to generate and check numbers entirely. Instead, it leverages combinatorics to directly calculate the result with a time complexity of n. This represents a significant improvement, especially as n grows larger. Finally, let's mathematically confirm the efficiency of the current approach. The for loop executes n1 iterations, and since each iteration involves only constant time operations, the total time complexity is n. On the space complexity side, the function operates with a fixed number of variables such as count, unique underscore digits, and available underscore digits, which do not depend on n. Therefore, the space complexity is 1. Together, these findings demonstrate that the function achieves linear time complexity and constant space complexity, making it not only efficient but also scalable for the problem's requirements. This combination of low time and space complexity ensures the solution is well suited for practical use cases. Now, let's go over some common mistakes that can occur when solving this problem. One frequent issue is off-by-one errors in loops, which happen when you forget to account for edge cases. For example, you might miss numbers with fewer digits than n, or mishandle boundary conditions, like whether to start counting from 0 or 1. This can lead to either missing valid numbers or including invalid ones in your results. Another common mistake is failing to check for leading zeros. If the problem specifies that numbers with leading zeros, such as 0, 1, 2, 3, are invalid, then including these would be considered an error. This is especially important in scenarios where real-world constraints apply. Additionally, errors in validating duplicate digits can occur. For example, using inefficient nested loops or neglecting to check all digits can lead to incorrect outputs or drastically increased runtime. Finally, overlooking constraints is another major pitfall. If you don't optimize for large values of n or fail to handle cases like n equals 0, you may encounter performance issues or even runtime errors. Keeping these mistakes in mind and addressing them early can save a lot of time and effort. Let's discuss another common error: incorrect complexity analysis. Misjudging the time complexity of your solution can lead to poor decisions about which approach to use. For instance, you might dismiss a brute force solution prematurely or fail to optimize an already efficient solution for interview follow-ups. Speaking of interviews, there are several insights to keep in mind. Recognizing patterns in digit selection is crucial. For example, the first digit has 9 possible options if we exclude 0, the second digit has 9 remaining options, and so on. Understanding this pattern can simplify your approach significantly. Interviewers are also keen to see how you optimize brute force solutions. This might involve skipping numbers with duplicate digits early in the process to save time. Additionally, always explicitly address edge cases, such as when n equals 0, n equals 1, or when n reaches its maximum allowed value. Finally, be prepared for follow-up questions that introduce variations to the problem. For instance, you might be asked how to handle digits forming a palindrome or allowing repetitions. These variations test your adaptability and your ability to apply the underlying concepts to new scenarios. To deepen your understanding, it's helpful to explore related problems. For example, LeetCode 47, Permutations 2, focuses on handling duplicates, while LeetCode 90, Subsets 2, deals with unique constraints. LeetCode 266, Palindrome Permutation, introduces the concept of forming palindromes, which could tie into potential variations of this problem. Each of these problems helps build a broader skill set for similar challenges. Now, let's consider some alternative approaches. The mathematical approach relies on combinatorics to reduce time complexity. While it's efficient, it does require a solid grasp of mathematical principles, which might not be intuitive for everyone. Backtracking is another option, particularly useful for generating permutations directly. However, it becomes less efficient for larger values of n due to the overhead of recursion. Finally, there's bit masking, which is particularly efficient for tracking used digits, especially in problems with additional constraints. However, bit masking can be more challenging to implement and debug, especially for beginners. Each approach has its trade-offs, so it's important to choose the right tool for the problem at hand and your level of comfort with these techniques. Great job! Today, we tackled count numbers with unique digits. This problem emphasized combinatorics and algorithmic efficiency. Remember, brute force is a good starting point, but optimization is key. Thanks for watching. Be sure to like, subscribe, and keep coding. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!